Hello class, this is the Unit 7 review. 3 years ago, the mean price of a single-family home was $243,765. A real estate broker believes the mean price has increased since then. We want the null and alternative hypotheses. So the null hypothesis would be that the mean is $243,765. And the alternative is that the mean has increased, so it's greater than $243,765. So then we are asked about what it would mean to make a type 1 error. So if you recall, that is when we are rejecting the null hypothesis when it is indeed true. So the broker rejects the hypothesis that the mean price is $243,765 when the true mean price is greater than $243,765. Again, this is from rejecting the null hypothesis when it is true. This is rejecting the null hypothesis when the null hypothesis is true. And then what would it mean to make a type 2 error? So in that same idea, this is where we fail to reject the null hypothesis. To reject the null hypothesis when the alternative is true. So what does that mean? That means in this case, the broker fails to reject the hypothesis that the mean price is $243,765 when the true mean price is greater than $243,765. Question number 2, we have suppose the null hypothesis is rejected. State the conclusion based on the results of the test. 3 years ago, the mean price of a single-family home was $243,753. And real estate broker believes the mean price has increased since then. So, for the null hypothesis is rejected, this should be there is not sufficient evidence to conclude the mean price of a single family home has increased. Due to the fact of that null hypothesis being rejected. Excuse me, since the null hypothesis is rejected, there is sufficient evidence to conclude that the mean price has increased. Since we are rejecting the null hypothesis, this would be in terms of favoring the alternative. So here we are favoring the alternative, which in this case will be that there is indeed sufficient evidence to conclude that the mean price of the single-family home has indeed increased. The third one, we have gone to a food website. The mean consumption of popcorn annually by Americans is 56 quarts. The marketing division of the food website unleashes an aggressive campaign designed to get Americans to consume even more popcorn. we want the null and alternative hypotheses that would be used to test the effectiveness of this marketing campaign. The null hypothesis would be that the mean is 56 quarts, and the alternative would be that the mean is greater than 56 quarts. For part B, a sample of 801 Americans provides enough evidence to conclude that the marketing campaign was effective. We want to provide a statement that should be put out by the marketing department. There is sufficient evidence since the campaign was effective, which means the mean was greater than 56. So there is sufficient evidence to conclude that the mean consumption of popcorn has risen above 56 quarts in this case. Now, let us suppose, in fact, the mean annual consumption of popcorn after the marketing campaign is 56 quarts. Has a type 1 or type 2 error been made by the marketing department? If we tested this hypothesis at the 1% level of significance, what is the probability of committing this error? So, since we are claiming that we could reject the null hypothesis, when indeed the null hypothesis is true, the marketing department, I should say, committed a type 1 error because the marketing department rejected the null hypothesis when it was true. The probability of making a type 1 error is that level of significance, which was 1%, so as a decimal, that is 0.01. For question number 4, we want to determine the critical value or values for a left tail test of a population mean with a 5% level of significance with a sample size of 20. Since the sample size is 20 here, our degrees of freedom will be 1 less than that, so in this case, 19. So we want to find this critical value. This is the probability we have some t-value that's less than whatever we get is equal to 0.05. So that looks like this. A mean of 0 here. 0.05 would be down here-ish. So this value we need to find through StatCrunch. So we are going to go to Stat, Calculators, and then T. This uses a degree of freedom of 19. And we want the probability less than whatever the value is to be 0.05. This gives us for an answer negative 1.729. Negative 1.729. For the two-tail test of a population mean at the 1% level of significance based on a sample of size 19. So this one would decrease in 19 by 1 to get 18 for degrees of freedom. And this one, with a 0 right here, we want the value above it, above positive t and below negative t. But those two add up to be the 1%. So this is the probability we have a t-score that is greater than the absolute value of t is equal to 0.01 in our case. So for this one, we are getting ourselves two answers, a positive and a negative version. Is there a best way to do this? No. There's more than one way to do it. But I'm going to put in the degree of freedom of 18. And since the area on either side, they need to add up to be 1%. The area on either side is half of 1%, so 0.005. And that gives us a value of 2.878 that rounds to. So that means it's positive 2.878 on the right-hand side and negative 2.878 on the left-hand side. Moving along, question number 5. In a study, researchers wanted to measure the effect of alcohol in the hippocampal region, the portion of the brain responsible for long-term memory storage, in adolescents. The researchers randomly selected 24 adolescents with alcohol use disorders to determine whether the hippocampal volumes in the alcoholic adolescents were less than the normal volume of 9.02 cubic centimeters. An analysis of the sample data revealed that the hippocampal volume is approximately normal, with X bar to be 8.15 cubic centimeters, S to be 0.8 of a cubic centimeter, and we want to conduct the appropriate test at the 1% level of significance. This uses the null hypothesis, where the mean is 9.02 cubic centimeters, and the alternative, where the mean is less than 9.02 cubic centimeters. We want a test statistic. So the whole spiel to do with this, the mean of 0. Our critical region would be, since this is on the left-hand side, someplace down here, matching the 1% level of significance. So let us calculate that in StatCrunch. For this, we are going to go to stat t-stats, one sample with summary. The mean we are using is 8.15. The sample standard deviation of 0.8. Sample size of 24. And we are doing this test with the value of 9.02, and the alternative is a less than symbol. Doing so provides us this test statistic is negative 5.328 in our case, and the p-value is less than 0.001. But on the test, they'll make you round that to 3 decimals. But test statistic here is negative 5.328, which then indicates it falls within our critical region here to be in this case, sufficient evidence. The p-value, though, since it was less than 0.0001, will just be rounded to 0.000. And then we want to make a conclusion regarding this hypothesis. Well, we are going to reject the null hypothesis. So there is sufficient evidence. Sufficient evidence to claim that the mean hippocampal volume is less than 9.02 cubic centimeters. For question number 6, the mean waiting time at the drive-thru of a fast food restaurant from the time an order is placed to the time the order is received is 84.9 seconds. A manager devises a new drive-thru system that he believes will decrease wait time. As a test, he initiates the new system at his restaurant and measures the wait time for 10 randomly selected orders. The wait times are provided in the table. Because the sample size is small, the manager must verify that the wait time is normally distributed and the sample does not contain any outliers. The normal probability plot is shown, and the sample correlation coefficient is known to be R is equal to 0.985. We want to know other conditions for testing the hypothesis satisfied. So for this, we know our sample size here is 10. And one of the conditions that we need to check is whether or not we actually have a linear relationship. We could kind of see it going down here in the normal probability plot, but yet we could also determine it from this critical value. So on the test, they are going to provide to you this table, which is the correlation coefficient critical values table. And we base it on our sample size. Our sample size in our sample here was 10. So we're using this row here in this case. We'll be talking more about this in Unit 8. Well, the sample size of 10, critical value is 0.918. And then with regards to this critical value, the absolute value of the correlation coefficient, 0.985, is supposed to be greater than this. And as we could see, it is. It's greater than 0.918. So because of that, this should be one of these, oh yes, the conditions are indeed satisfied. So let us write that. Yes, the conditions are satisfied. The probability plot is linear enough. By the way, when I say linear enough, probably should make note very quickly that this is pretty much a straight line. There's a little bit of variation here at the end, but most of these data points are indeed in a straight line. That's what that means by linear enough. Since the correlation coefficient is greater than the critical value. And again, that was from what we just found a few moments ago based on that critical number table. In addition, a box plot does not show any outliers. You do not need to try to utilize that box plot. If you wanted to, I could show you what that looks like and stat crunch very quickly. This is the data. If you wanted to verify that using a box plot, as underneath graph, box plot, you would choose the variable and you would look at the box plot, which does not show any outliers based on our fencing that we would normally use. So because of that, conditions are satisfied. Moving on, we ask, is the new system effective? We want to conduct a hypothesis test using the p-value approach and a level of significance of 10%. So the null hypothesis that we are using is that the mean is 84.9. And the alternative is that the mean is less than 84.9. So opening back up StatCrunch, we are going to go to stat, t-stats, one sample with data. Choose a one variable. The hypothesis statements involved 84.9, and this is a less than symbol. Here's our test. So our test statistic is negative 1.303, and the p-value is 0.112. So let me write that down. Test statistic is negative 1.303, and the p-value, I'll write that down here, p-value is 0.112, which, I mean, let's face it, it's pretty high, right? That's 11% with a level of significance of 10%. So yes, pretty high. The p-value is greater than the level of significance. So there is not sufficient evidence to conclude the new system is effective in our case. For number 7, we have 1 year. The mean age of an inmate on death row was 41.4 years. Sociologists wondered whether the mean age of a death row inmate has changed since then. She randomly selects 32 death row inmates and finds that their mean age is 40.8 and a standard deviation of 9.5. We want to write the hypotheses. So the null hypothesis is that the mean is 41.4, and the alternative is that the mean is not 41.4. For the 95% confidence, we can find our lower and upper bounds. So let me pull that back up, get rid of all this. We're going to go to stat, t-stats, one sample with summary. The sample mean was 40.8 years. Sample standard deviation was 9.5 years. Sample size was 32, which is good for our case. And we want the 95% confidence interval. That provides a lower limit or bound of 37.37 years and an upper bound of 44.23 years. Let me write those down. 37.37 and 44.23. So how do we describe that? This should be with 95% confidence. The mean age of a death row inmate is between 37.37 years and 44.23 years, according to this data. And then we want to know, what does this interval imply? Since the mean age from the earlier year is contained in the interval, there is not sufficient evidence to conclude that the mean age had changed. Let me know if you have any questions or concerns. Thank you.